Hello everyone, and welcome back to physics. Our lesson today is on conservative and non-conservative forces. A link to this PowerPoint file can be found on our class homepage, and I encourage you to print that out and take notes in the margins, or if you'd like, just take notes in your notebooks. So far in our study of mechanics, we have looked at the law of conservation of energy. And we've looked at some simple problems in which we've assumed that the total mechanical energy of a system remains constant. So for an example, we've assumed that in a problem with a roller coaster, if the roller coaster is at the top of a hill, that all of its potential energy would be converted into kinetic energy at the bottom of the hill. Now, is this a realistic assumption or not? Well, it depends. And so we're going to become more sophisticated today by understanding the difference between conservative and non-conservative forces and the role that they play in this problem. So let's start off by defining conservative forces. A conservative force is always associated with a specific form of potential energy. We will see three major examples of conservative forces this year. The first example that we're already familiar with is weight. Weight is associated with the form of potential energy known as GPE, or gravitational potential energy. Two other examples that we will meet are the restoring force and the electrostatic force. The restoring force is the ideal restoring force exerted by a spring on an object when the spring is either stretched or compressed. Now, when you stretch or compress a spring, you store potential energy. And that's given by a new formula, EPE, which we're not going to worry about right now. The same thing can be said for the electrostatic force, which we'll meet in the second semester. You can store energy in an electric field by pushing a charge one way or the other in an electric field, and we'll be studying that the second semester. But the main point is that all three of these forces have potential energies which are connected with them. So one of the ideas here is that when a conservative force does positive work on an object, the corresponding potential energy decreases by the same amount. The math way of saying it is that the positive work done by a conservative force is equal to the negative of the change in the potential energy. And you can think about that second part, or the right-hand side, as meaning a decrease in potential energy. So an easy example is that something might fall. When you think about an object which freely falls x meters. If something falls, gravity does positive work on it, equal to positive mgx, because of force times distance. If something falls, we know its potential energy, though, is also going to decrease by an amount equal to negative mgx, because its height is decreasing. Here's a picture of that situation. Assume that you have a box that falls from a height of 10 meters. The box might have a weight of 1,000 newtons, and it might fall that particular distance of 10 meters. And we understand that in this situation, first of all, gravity is going to do positive work on the object, because gravity is pulling down and the object is moving down. And we also understand from energy conservation that the object will transform GPE into KE. So here we see that the work done by the conservative force of gravity, in other words, 1,000 newtons times 10 meters, is a total amount of a positive 10,000 joules. This number of joules is actually the amount of potential energy that is decreased for the box as it falls. By the work kinetic energy theorem, we know that the work done by the conservative force of gravity is also equal to the net work, because there is no other force acting on the box in this particular case. So a net amount of work of 10,000 joules is done on the box, and by the work kinetic energy theorem, we know that the kinetic energy increases by 10,000 joules. And this makes sense with what we know about energy conservation. Mechanical energy is conserved perfectly in this situation where you have an object in free fall. So hopefully you can also see that conservative forces like gravity do zero net work on objects that undergo a round trip, objects which start and end at the same point along the relevant potential energy coordinate. In other words, if the box were to rise back up to its starting point in the previous example, gravity would do a negative amount of work on the box equal to negative 10,000 joules, because the box is going up and gravity is still pulling down. So overall, gravity would have done a total of 0 joules of work on the box when it returns to its original height. Now let's consider non-conservative forces. The work done by a non-conservative force causes changes in non-mechanical forms of energy. That is, forms of energy other than potential and kinetic. The major example of a non-conservative force that we're going to encounter in this course is friction. Friction is great at converting mechanical energy into thermal energy, and sometimes we call this heat. There are other forces too that act in a non-conservative manner. When we talk about the force exerted by a person's muscle, this is a very typical type of a force in a physics problem. And this type of force is good at converting chemical energy into mechanical energy. And again, the idea is that chemical energy is not mechanical. There can be other effects from non-conservative forces. They can cause permanent deformation, or they can produce non-mechanical forms of energy such as light and sound. In fact, there are far more non-conservative forces in the universe than there are conservative. So let's return to our original example of an object that's falling, except now we're going to add a drag force. Okay, so you can think about this as air resistance or fluid resistance. And we'll assume that that force has an average upwards value of 200 newtons. So our understanding from conservation of energy is that the object will start with gravitational potential, and it will end with kinetic energy. However, its final energy will have to split between kinetic energy and thermal energy, because the effect of the drag force will be to cause thermal energy to be generated as the object falls. So we're going to expect the object to have less kinetic energy at the end of its fall. If we look at the work done by the conservative force of gravity, it's still equal to positive 10,000 joules. No change there. We still see that the object has lost potential energy of negative 10,000 joules, just as it did before. However, now when we consider the non-conservative force of friction, we see that it does negative 2,000 joules of work. Do you know why? Well, first of all, it's negative because friction goes up when the displacement of the box is down. So opposite force and displacement mean negative. And 2,000 comes from the fact that you've got 200 newtons acting over 10 meters. Now, this leads to an increase in thermal energy exactly of 2,000 joules. In other words, 2,000 joules of thermal energy have been added to the system. Coming back to the work kinetic energy theorem, we now see what we expected. In other words, the total amount of work that's done on the box has been reduced. It's no longer 10,000 joules, but it's only 8,000 joules. And you can see why it's so important for us to consider the negative sign when we talk about the work done by friction. This 8,000 joules is the amount of work that's left to make up the object's final kinetic energy. And you can see that the object has less kinetic energy at the end than it did without air resistance. This means that the object won't be moving as fast, and it means that we've basically taken 2,000 joules of energy and converted it into the heat. So a couple of final points on this. For non-conservative forces, you can hopefully see that the round-trip work is never going to be equal to 0. In other words, if somebody actually were to bring the box back up to its starting point in the previous example, we would actually generate more heat in the process. The heat wouldn't cancel out. And therefore, you can never have thermal energy canceling itself out. So the round-trip work done by friction would never be equal to 0. In fact, the longer the path that the object follows, the more heat that gets generated. And so we say that the work done by friction depends on the path. And finally, hopefully you've noticed that friction can only do negative work. And this work is equal to the increase in the thermal energy for the system. For this reason, friction is called a dissipative force. Not all non-conservative forces do negative work only, but friction is the most important example of one that does. So one of the interesting things to look at here, to tie things together, is to come back to the law of conservation of energy. In fact, if you remember, the work kinetic energy theorem says that the net work done on an object is equal to a change in its kinetic energy. If we consider the fact that net work is really made up of the work done by conservative forces plus the work done by the non-conservative forces, then we can say that the sum of those two works is equal to the object's change in kinetic energy. If we then substitute the fact that the work by conservative forces is equal to a decrease in potential energy, and the work done by non-conservative forces is equal to the change in other forms of energy, we find a new expression which we can rearrange, and we find that if we look at the change in every form of energy of the object, and we add together all of the changes, positives and negatives together, in fact they should cancel each other out perfectly and give us a result of 0. And this is actually another way of looking at or stating the law of conservation of energy. So we'll come back to the two examples that we've looked at so far. These are all the same details that we've discussed, but take a look at the changes in potential and kinetic energy for example 1. If you add together negative 10,000 joules and positive 10,000 joules, you come up with the total overall change of 0. Energy was conserved. Similarly, if you look at the second example, falling with air resistance, and now you consider the change in potential, the change in thermal, and the change in kinetic, again you find that when you add all three together, you get a total of 0 joules. And therefore, that means that energy is conserved for the whole system. So looking at the change in energies and adding them up, the fact that they add up to 0 is just another way of saying that energy is conserved. In this third example, I'm not going to go into a lot of detail here, but I just wanted to give you an example of where muscle power is important. And this is an example of a person pushing a crate up an inclined surface. A man pushes the crate with a diagonal force of 700 newtons. The force of friction works against him at 50 newtons, and weight on the object is 1,000 newtons. And what you can do is the same sort of accounting. You can determine the work done by the man, which is positive, the work done by friction, which is negative, and the work done by gravity, which is negative in this case. And it turns out that the net work is 250 joules. If you then look at the corresponding changes in different forms of energy, you see again that they add up to 0. And what's interesting here is in the case of the man, the work that he does corresponds to a decrease in the chemical energy of the system, because he had to eat some breakfast to do the work that he did. And so here when we have muscle force, we're talking about a decrease in chemical energy. So to summarize what we've seen here, we can say first of all that conservative forces are always associated with specific forms of potential energy. Secondly, we can assume that mechanical energy is conserved when only conservative forces act. Non-conservative forces transform energy into non-mechanical forms. Friction is the most important non-conservative force, and it converts energy into thermal forms. So coming back to the original idea of the roller coaster, we can now see that to assume that mechanical energy is conserved, that is, that all potential energy is converted into kinetic energy, is probably unrealistic. And a more realistic treatment would be to consider the roles of non-conservative forces, especially that of friction. This is actually a fairly difficult thing to do in practice, and so for the most part for problem solving we're going to assume that only conservative forces act and that mechanical energy is generally conserved. But you should be aware of the fact that in real life we always have non-conservative forces acting, and it's something that is sometimes more important than others. Okay, well I hope you enjoyed this lesson, and I will see you tomorrow. Bye-bye.